Let's talk about the fundamental theorem of vector line integrals. Now, this is going to be the beginning of a series of theorems that will culminate in what's called the generalized Stokes theorem. It's one of the most beautiful theorems in mathematics. Okay? And you'll recall from earlier calculus courses what the fundamental theorem of calculus is. And it basically tells you that if you take the integral from a to b of some derivative of a function, then it's actually equal to that function, the antiderivative, right, of df dx, fb minus fa. More broadly, of course, any antiderivative that respects this property there would do. Okay, and what you could basically translate that language as is that you could trade a derivative in the bulk. Okay, so the bulk is a to b and everything in between. Okay, so you could trade this integral of the derivative in the bulk of AB for an operation at the boundary of AB. Now this symbol here means boundary of the interval AB, and you get the set of points A and B. So this, you're just left with the point A and B. So you could trade a derivative in the bulk for an operation at the boundary. That's the sort of the core of what the fundamental theorem of calculus is telling us, and we will get similar theorems for all sorts of derivatives, and among them are gradients. Okay, and this is why we were so interested in conservative fields, because if a vector field is conservative and you satisfy some basic properties in this theorem, then what you could do is write f as equal to the gradient of phi dot dr, right? And you could trade this derivative here of phi for an operation at the boundary. Okay, so you could trade a gradient in the bulk between a and b on this curve C for an operation at the boundary, subtracting phi at this point here, b, minus phi at this point there, a. Okay, and in this sense, phi is somewhat like a antiderivative of the vector field f, if you will. So this is the fundamental theorem of line integrals. Okay, and we go through a sketch of proof over here. If we have a parameterization that starts at a and ends at the point b, starting at time little a and ending at time little b, we could take the derivative of phi with the parameterization plugged in, and we could use the chain rule, write that expression as a dot product between the gradient of phi and r prime. And now this should look familiar, since the line integral of f is equal to this function here, and we just showed that this guy here is equal to d phi dt with the parameterization plugged in. And so from the fundamental theorem of calculus, you could write this as phi rb minus phi ra, and you get your result there. So we used the fundamental theorem of calculus to prove the fundamental theorem of line integrals. Okay, and now this could make computing line integrals infinitely easier. So evaluate this line integral here, where c is a straight line from a to b. Now if we want to do this directly, the direct route of just computing this line integral, then we'll have to parameterize the curve from a to b and plug it into the formula and the procedure that we've outlined before. But we know something about this vector field. Okay, this vector field is conservative, and we actually computed the potential for it. Okay, so if you want to check, take the gradient of this function and you will get this vector field. Okay, so what we're going to do is instead use the fundamental theorem of vector line integrals to compute this. So we know that this is equal to the gradient of the phi, right? This here is phi, okay? The gradient of phi dot dr. And we know from the fundamental theorem of vector line integrals that that's just equal to phi b minus phi a. Now what is b? B is 1, 2, 3. What is a? Negative 3, negative 2, negative 1. And so you have that right there. Now you just plug in that point 1, 2, 3 into your scalar function, and you plug in the point negative 3, negative 2, negative 1 into the scalar function. Notice here I didn't even plug something for the I just left the const like constant. I mean, you could set it equal to 0 if you would have liked, but no matter what you set it to, it would subtract. These two will always subtract. Okay, so there was no worry that if you add a certain number, okay, like a real number, to your potential, that it would mess up answers. They'll always cancel each other out with that minus sign there. And you get 16. And that is so much easier than doing the direct line integral, thanks to using the fundamental theorem of vector line integrals.